I can do it. Okay, so I'm assuming you guys watched the introductory buffer lecture. That just sort of runs through the basics of buffers. There's sort of just a couple calculations that I want to make sure everybody's very comfortable with, because these are the mathematical equations or the mathematical problems that you'll be dealing with 99% of the time. There'll be other calculations in the future, but 99% of the time of what you're doing in biotech or molecular biology or in my lab is going to be these very simple calculations. So I just want to go through those and make sure everybody understands those. So the first calculation is molarity, calculating like the molarity of how to make certain molar solutions. Okay, so if I was to ask this question, like it would come up in a situation like this. So the way that this would come up is so the problem is I need to make a stock solution of something, let's say, of 1 molar sodium chloride. That's a very common thing. That might be like actually the first solution that you make. If I asked you to do this, so here's actually a question I'll pose to you. What would be the first thing that you would do in the algorithm? What's the first thing that you need to do? Step 1. This is not a rhetorical question. Actually, try to answer this.
Determine the molecular weight of the chemical.
Yeah, that's right. Okay, so you need the molecular mass. So collect the molecular mass. How would you get that?
The periodic table.
So that's going to be not the best way. So you might think to go to the periodic table and then you'd like calculate the mass of each element and then you'd add them up. That's actually not the best way, because many times when you're dealing with solutions, you're actually not always dealing with the exact atomic weights of the solution. Sometimes there's like water molecules, sometimes there's other things attached. So getting the molecular mass from the periodic table, while that seems theoretically good idea, that's not the way that you should do this. Any other ideas? I did not hear that, if that was a response. Or is the response, no, I don't know what to do?
Oh, you can also find it on the label.
Yes. Okay, so that's the correct answer. So the answer is look at the label on the bottle. That's what you want to do. You might be tempted to go to Google, or you might be tempted to go to AI, which is actually what I'm going to go to test this. That is a intermediate okay solution that might actually give you problems in the future. The best thing you need to do is look at the bottle. And again, the reason you want to look at the bottle is because there's different variants. And so you might actually see different variations in the molecular weights of these items that you're working with. So let me just actually get it. What is the molecular weight of sodium chloride? Let me see if it can give it to me. 58.44 grams per mole. Let's just check Google. Molecular weight of sodium chloride, 58.44. Okay, so again, if I'm using like internet resources, I will always cross-check, just double check. But the best solution is looking at the bottle. So for us, 58.44 grams per mole. Okay, so then the next question, step 2. What do you do next? Clearly.
Dissolve it in 1 liter of salt.
So you said something about 1 liter of water. What with 1 liter of water?
Dissolve it?
Yeah, okay, but what? Dissolve what? Speak more
dissolve
precisely.
the sodium chloride
How
powder
much?
into
How much?
precisely 58.44 grams.
Yes. Okay. So this might be simple, but again, okay. So this might be too simple for you guys, but we're starting at the basics just so that I make sure that like everybody understands. And again, this is the most common thing that you'll be doing. So that's why I think this is important to have a solid foundation. So yes, the key thing is if you want a 1 molar. So if you want 1 molar, the definition of like a 1 molar solution is going to be the molecular mass. So it will be the molecular mass per 1 liter of water. So that would be 58.44 grams. You'd weigh that out, and then you would put that and you dissolve it in 1 liter of water. But let's actually like talk about this just a little bit more. One common problem is that people will fill up 1 liter of water and then they will add the powder. That's wrong, because that will increase the volume. So always add the powder and then add the solution, the water, to 1 liter, and then you can dissolve it. What if I wanted 0.5 molar? What would you do then?
If you wanted 5 molar, is that what you said?
0.5 molar.
0.5 molar. Oh. Divide 58.445 half.
Yes. So you'd take half this. So it'd be
Yeah.
that divided by 2. Or if the other thing you said is 5 molar. If I wanted 5 molar, yes, if you wanted 5 molar, in contrast, you would multiply that by 5. Again, I'm not showing this because it's complex. I'm showing you this because it's easy and it's the most fundamental thing you will do. And so if you do this wrong, you would never succeed. So I'm just showing that to so everybody knows that. Okay. So we know how to make a 1 molar solution, a 0.5 molar, a 5 molar, etc. So this is how you're going to be making your stock solutions. Then the next question is, okay, so that's very easy. The next question is, let's say I made a 1 molar solution of sodium chloride. A common thing now, so that's what you would call a stock solution. That's my stock solution. So then the most common other thing that you will do is, let's say I ask you, you need to make working solution of 0.1 molar sodium chloride in 100 mils volume. How do you do that? Do you guys know how to do that? How to figure out or how to calculate that? I think I do talk about this in the lecture, but I didn't do an example, which is why we're doing this. So there is a formula.
C1 V1 equals
Yes.
C2.
Okay. So that's what you're going to be doing. And again, like that's 99% of the calculations in molecular biology that you'll do is the CV. Let's see. CV11 equals CV22. So this is a proportional equation. This is the simplest calculation, the simplest way to do this. So you have a concentration that you know, which is 1 molar of your stock solution. And you have a concentration that you want, which is 0.1 molar. Okay. And you know the volume that you want. That's volume 2. You know you want 100 mils, which is 0.1 liter. You got to be careful about the units. Okay. And then the question is how much X? That's the question. That's the variable we need to calculate. How many liters of that 1 molar do you need to add to get this final concentration? So to simply do this math, 1 times X, that's X liters equals 0.1 times 0.1. But you would just shift the decimal place over. 0.1 times 0.1, as an example, 0.01. 0.01, okay? So the amount that you would add of the 1 molar stock is 0.01 liters, okay? So that would be 10 milliliters of 1 molar solution. You would add 10 mils. So if you have like a beaker, you would add the 10 mils. So now you have only filled it 10%. It's 10% full at this point. And then you would, because you want 100 mils volume, you would quench the solution, QS, quench the solution to 100 milliliters. So then you'd take water and you would add water, fill it up to the 100 mil mark. Probably best to use a graduated cylinder. Does that make sense? Is that easy? Like we understand how to do that?
Confirm.
Yes.
Okay, good. Again, this is not doing hard stuff yet. We're just doing easy stuff. Okay, the other reason that you might use the CV equation, that's the most common example of this. You'll see the CV equation come up a ton. Another common thing is to calculate or standardize optical density, OD, of cell cultures, usually bacterial cells. So for example, one example would be, this is example 3. You grow a solution of bacteria overnight. So let's say you have a beaker, or a test tube, rather. You have a test tube, you put 5 mils of LB, Luria broth. You inoculate that with bacteria. You let it grow overnight. It grows to density, high density culture overnight. And let's say then the next day, you're going to do an experiment. And you want to know precisely how many cells are in your experimental tube. So the next day, you measure the OD, which is the optical density using the spectrophotometer. I'll train you how to do that later, but for now, we'll just talk about the calculations. So you'd measure the OD, and let's say you measure that OD, and let's say you get a reading of 2.5. So the optical density at 600 nanometers is 2.5. And you want one standardized OD of cells in 1 mil of the culture. That is the next scenario that you would use the CV equals CV. So to do this calculation, simple calculation, the concentration that you know is 2.5 ODs, and you want to know how much of that volume to add to create a new solution that is 1 OD in 1 mil. Again, careful about your units, but it's the same calculation. So it's just 2.5 x equals 1 mil, x equals 1 divided by 2.5. I always check, even if you do things by hand or by mind, I always will like double check my calculations. 0.4. And the units are mils in this case. So 0.4 mils is 400 microliters. So in this case, you would take 400 microliters of that. You would put it in a Eppendorf tube, 400 microliters, which is about to there. And then you would add 600 microliters of water to generate the 1 OD culture of 1 mil volume. Does that make sense?
Yes.
Okay. Let me stop recording. Hang on. The button has disappeared.